For this unit, we're going to skip ahead to Chapter 9, and we're going to talk about financial mathematics. And there's a lot of real neat math that goes into financial mathematics. We're going to start simple today by calculating a balance and the interest on a lump sum payment. And as we work through this unit, the common question I get is, I know how to solve all the problems, I just don't know which equation to use. Well, the key here today is we're talking about lump sums. All the money is going to be talked about at the same time. It's going to be different than like when you're paying off a loan and you make payments every month. So today we're focusing on a lump sum. And to kind of set this up, we're going to do a couple definitions. Make sure we all know what we're talking about when we use some of this vocabulary, because some of this vocabulary is new in the terms of the financial world, depending on how much you've worked with it. Things like the word interest. Interest is the rent, if I can use that term loosely, paid for the use of money. The idea here is I'm going to let you use some of my money, you're just going to pay me interest, pay me rent to use that money. So it's money on top of the amount borrowed or given. Another word we're going to use a lot is the principal. Or sometimes you'll hear me say present value. They both mean the same thing. The principal or the present value is the amount of money borrowed or loaned. It's the value of the money right now. If I loan you $100, right now the present value of that money is $100. You're going to pay me back more later. That's a future value, what you're going to pay me back. But right now, the amount borrowed or loaned is the present value. And the most basic way we have to talk about interest is this idea of what is called simple interest. Simple interest is interest earned only on the principal. Interest on principal only. So however much you borrow, that's what you're going to pay interest on, not any type of growing amount. And to help us work with simple interest, we've got a couple equations that we're going to look at. The first equation is I equals P R T. I, in this case, stands for the interest earned or paid. P is going to stand for the principal or present value of the loan. R is the interest rate. So if you pay a 6% interest, R would be 0.06. We have to change that percent into a decimal. And finally, T is time. And that time has to be in years. That's really important. Time is always in years when we're talking about these investments. The other equation we're going to use is if we are interested in some future amount, how much is going to be paid back at the end of the loan, or how much the investment is worth, we're going to use the equation A equals P, the principal, plus the interest. Or maybe a better equation would be if I replace I with what it represents, doing a substitution. I is PRT. And in fact, to make it even better, we could factor out the P. And so we get A equals P times 1 plus RT. And a lot of the same definitions. The new variable here is A, which stands for the accumulated amount. The amount that's there at the end, it is the future value. So P is the present value, the starting, A is the future value, the finishing amount. So just to make it really clear, the two big equations we're going to use about simple interest, I equals PRT, and A equals the principal times 1 plus the rate times time. So let's do some examples and see if we can calculate some interest problems. Let's say $800 is borrowed for 8 months at 13% simple interest for 2 years. Oop, I'm sorry, I get my examples mixed up. At 13% simple interest per year. We already know the 8 months, don't need a different time in there. We're going to find the interest and the amount owed at the end of the 8 months. Well, to find the interest is I equals PRT. We don't know the interest, that's what we're trying to find. Why don't you do this stuff in green? Equals P. P stands for the principal or starting amount, present value that is borrowed. That is the $800. $800 is borrowed. R is the interest rate. R is that 13%, but we have to write it as a decimal, which is 0.13. Times T. T is the time of 8 months. But remember, time has to always be in years. So what we're going to use for time is 8 divided by the number of things in a year, divided by the number of months in a year, which is 12. So we're going to use 8/12. And we can type that into our calculator, 800 times 0.13 times 8/12. Actually, let's look at how we do that on the calculator. So here I've pulled up, it kind of cuts off the top because the screen's too small here, but I've pulled up a TI 84 Plus Silver Edition calculator. It's just like the TI 84, the 83, the 85 is also similar enough that you can follow along. So to find the interest, we're going to take 800, 800, times the 0.13 times the 8/12. And the way we get the twelfths is we use the fraction bar, 8/12. And when we hit enter, we find out the interest there is 69.33. So 69.33. Rounded to the nearest dollar, that is the amount of interest we've earned. Now if we started, or that is owed I should say, if we started with 800, to find out the amount owed, we have to pay back the 800 and we have to pay back the interest. So the amount owed is the principal of 800 plus the interest of 69.33. So the amount that is owed is $869.33 is what is paid for the privilege of using this $800 for 8 months. And that's how we can calculate simple interest. Let's do a couple more problems to get a really good grasp of what simple interest is and how it works. Here's another problem. Let's say $1,500 is deposited at 8% simple interest. We want to know how much is in the account after 4 years. So here we're not so much asking about the individual interest. Here we are asking about the future value that's going to be there in 4 years. And future value, that was the A equals P times 1 plus RT formula. So plugging in what we know, A equals P, the principal present value, is the $1,500 that we started with, times 1 plus R, the interest rate, which needs to be converted to a decimal, 0.08. Be careful not to say 0.8, that's 80% interest. A great amount to earn if you can find someone who will pay it. 0.08, 8%. Oops, times the time. Oops. And the time is 4 years. So that's what we need to calculate then. 1,500, pulling up my calculator. 1,500 times, open up a parentheses, 1 plus 0.08 times 4, close the parentheses, hit enter. It looks like it says 1980. So the amount in the account is $1,980 after those 4 years. We can switch these problems up a bit and solve instead for one of the missing pieces. Instead of finding the present value or the future value, we can find a missing piece. So let's say if $4,800 is owed, which included 10% simple interest for 2 years. How much was borrowed? So here we're not so much, again, asking about the interest earned. We're talking about the future amount of $4,800 that is owed, the accumulated amount, based on the principal starting present value. So the equation we want to use here is A, the accumulated amount, the future value, is equal to P, the present value, the principal, times 1 plus RT. And if we look this time, we're talking about the $4,800, but that is the amount of owed at the end of the loan. That is a future accumulated value. So $4,800 this time is our A. Equals P, the present value of the principal that was borrowed. We don't know that. That's what we're looking for. Times 1 plus the rate. The rate is 0.10, 10%. Times the time in years, we are told, is 2 years. And we can do a little bit of algebra from here to solve. 4,800 is equal to P times 1 plus 0.10 times 2 is 0.20. And then when we add those, we get 4,800 equals, I'm going to put the number in front, 1.2P. Simple to solve for that present value. Divide by 1.2 to find out what P equals. 4,800 divided by 1.2. Oops, hit enter twice. That's okay. It's the same answer both times, 4,000. $4,000 was borrowed. Now, simple interest actually isn't used very often by banks and by mutual funds and stocks and all that. What more often where you see simple interest used is in the idea of discounts and proceeds. And that's what I want to look at next. Discounts and proceeds. And this is the idea of your typical payday loan company, which, by the way, is a terrible idea. And we can talk about why in class. But payday loan places work this way, and the idea is instead of paying an interest rate, the interest is paid up front. You write a check for $110, they pay you $100. And then it's yours. They don't cash the check till after your payday. So the idea of this discounts and proceeds is the interest is deducted at the time the loan is made. Again, I write a check for $110, and they give me $100 cash. So I've essentially taken a $100 loan, and then the $10 is the interest. I just paid it up front for the loan. A little vocabulary here, the amount deducted is the discount. So in my example with the $110 check, there's a $10 discount. I write a check for $110, but I only get $100. $10 discount. The amount given to the borrower is the proceeds. So that's my $100. Again, I write a $110 check, $10 discount, I get $100 proceeds. The amount paid back remember, it's a payday loan, so even though I've written the check already, it's not actually paid back until they cash my check after I get paid. The amount paid back is the maturity value. So that $110 check is the maturity value. So, again, we've got a couple equations with discounts and proceeds. Very similar to the simple interest equations. The first equation is that D is equal to MRT. Very similar to I equals PRT. Same idea. D here stands for the discount. M is equal to the maturity value. Maturity value is how much is paid back at the end. R is the rate. And T is the time. And again, time has to be in years. Of course, most often we're not interested in the discount. When you're getting one of these payday loans, what you're interested in is how much am I going to get, right? So that's our second equation. The proceeds, how much you get, is equal to the maturity value, but this time minus the discount, because the interest comes out up front. And in much the same way we played with these before, D, the discount, we found out was MRT, and we can factor that M out to get 1 minus RT. And so the only new variable here is P representing the proceeds. So again, two equations. That's not my highlighter. This is my highlighter. The first equation, the discount, is equal to the maturity value times rate times time. The amount of proceeds, what you get, is the maturity value times 1 minus the interest rate times time. So let's take a look at a couple examples where we play with discounts. How about $1,500 is borrowed at 13% for 9 months. We are going to find the discount and the proceeds. First, it asks us to find the discount. And the discount is equal to the maturity value times rate times time. So maturity value, the amount borrowed, that's the $1,500. Looking for the discount. $1,500 is going to be multiplied by the interest rate, which as a decimal is 0.13. And it is borrowed for 9 months. Now remember, time has to be in years, so we're going to have to divide by the number of months in a year. So that's 9/12 of a year. And so going back to our calculator, 1,500 times 0.13 times 9/12 is 146.25. Move this down a bit, actually. Let me show you the top of my calculator. 146.25. That is the discount. So I write this $1,500 check. They're going to discount at 146. What I want to know is the proceeds, how much I'm going to get. So 1,500 was the check. We subtract off the proceeds of 146.25. And what's that going to give us? 1,500 minus 146.25. I'm going to get a check for I'm going to get cashed $1353.75. $1353.75. So that's my proceeds after a $146 discount. Let's do one more with discounts. Let's say we've got a student who wants to receive $1,000. That's more the realistic situation. I know I want $1,000, so how much of a loan am I going to have to get to receive the $1,000? So I want to receive $1,000, let's say for 8 months at 14%. By the way, these payday loans charge ridiculous interest rates. 14% would actually be good at a payday loan place. How large of a loan should she ask for? So here what we're curious about, here what I want to know about are the proceeds, which are related to the maturity value. That's the loan we're going to ask for, times 1 minus RT. The proceeds, the amount that she wants to receive, is $1,000. That's my proceeds. What we're looking for is the maturity value, how much she's going to have to ask for, at 1 minus the interest rate, at a decimal is 0.14, times the time, which is going to be 8/12, because we have to change those months into years, right? And we're going to have to do a little bit of algebra to solve this, and our calculator is going to help us with it. I'm just going to type that whole big parentheses in the calculator, 1 minus 0.14 times 8/12, and hit enter. And I get 0.9066, maybe 67. And I'm going to show you a neat little trick, though, on your calculator to keep this as accurate as possible. We're going to divide by 0.9067 on both sides to get our M. Now, on the calculator, this is kind of neat. I can type in the 1,000 and divide, and then I want to divide by the number that is just above, that 0.9066666667. The way I tell the calculator to grab the number that is just above is we hit the second key in the top left corner, and then right above negative, you see it says A and S. Hit the negative, and it's going to give you the A and S. So that's 1,000 divided by the previous answer. Nice little trick to ensure we don't lose decimals. I want you to get used to using this because when we get into matrices, we're going to use that previous answer feature a lot. So I want you to know how to do that. Second, A and S. And when we hit enter, we find the original loan is 1102.94. 1102.94, the maturity value. If she gets a loan for 1102.94, she'll receive $1,000 cash to be paid back in 8 months when that payday loan place decides to cash the check. So that's how discounts and proceeds work. That's really the main place you see this simple interest idea worked out. In fact, we're not going to do a lot with simple interest because it's pretty straightforward. It's also not usually the best way to work with investments. It's also not often used in investments. What you see more often is you see what is called compound interest. Simple interest, you only earn interest on the principal. Compound interest, you not only earn interest on the principal, you earn interest on interest. Maybe we can clarify what that means a little bit. So here is the idea behind compound interest. You start, let's say, with $1,000 at 10%. Well, after 1 year, you get that $1,000 times 1 plus the interest rate. This looks kind of like the simple interest formula, right? 1 plus the interest rate of 0.10. But now the second year, you're going to earn that again. By the way, that equals $1,100. The second year, you're going to get everything that's in the account, but then you're going to get interest multiplied again because you're going to earn interest on the interest. And that gives you a total of $1,210. And this keeps going. In the third year, you get the $1,000 times the 1 plus 0.10 times the 1 plus 0.10. My hand can't keep up with me. But then we're going to earn interest again times 1 plus 0.10. And so now after the third year, you've got $1,331. And what's neat about this is the amount of your increase is increasing. So you're earning more money the longer you leave it in there. Notice the first increase, we earned $100. The second increase, we earned $110. The third increase, we earned $121. So the amount that we're increasing is increasing as well. We're earning interest on the interest. And so if this idea continues for t years, the idea is you get the $1,000 times the 1 plus 0.10, and we do that over and over again for the number of years. Well, repeated multiplication we show with an exponent. So we'll say 1,000 times 1 plus 0.10 raised to the t power. And then we can make this even more powerful if we compound the interest can be divided I should say the interest can be divided through the year. So your interest can be compounded not just at the end of the year, but it could be compounded monthly. A lot of bank accounts are compounded monthly, so the interest rate is divided into months. Or it could be compounded daily. Your student loans are often compounded daily. The interest is divided up by the day. It could be divided quarterly. If you do quarterly taxes and you owe money, you might be divided by 4. So it can be divided a lot of different ways. And so we end up with this final formula to get the future amount of your investment is based on the present value times 1 plus the interest rate divided by the number of compounds in a year raised to the number of compounds times time. And that exponent tells us how many times you earn interest throughout the year. Again, to clearly define these variables, A is the accumulated amount, or the future value. P is the principal, or the present value. Going off my page here. R is the interest rate written as a decimal. N, that's a new variable. N stands for the number of compounds a year. So if it's compounded monthly, there's 12 months in a year, N is 12. If it's compounded weekly, there's 52 weeks in a year, N is 52. And finally, T is time, and again, it's important that time is always in years. So here, whoops, gotta grab that highlighter better. Here is another equation that you're going to want to be able to use for this assignment. This is the compound interest formula, where we're earning interest on our interest. So let's take a look at a few problems that use compound interest. What am I on? 2? Let's say $2,500 is invested at 4% compounded weekly for 3 years. How much are we going to have? Well, when we see the interest rate is compounded, that means we take A equals P times 1 plus R over N to the NT power. A is what we're looking for, the future accumulated amount. P is the present value of the principal that we started with. In this case, $2,500 was invested, times 1 plus R, the interest rate. 4% as a decimal is 0.04. Divided by N, the number of compounds. It's compounded weekly. There are 52 weeks in a year. So N is going to be 52 raised to the NT power, and that's going to be 52 times time, which in this case is 3 years. So now we're ready to go to our calculator to find out how much money this is. Be careful at the calculator at the end here. I got to show you something. We got 2,500 times 1, make sure you open up a parentheses, plus 0.04 divided by 52, close the parentheses, and then right above divide there's this symbol called a caret. That moves us up into the exponent. Depending on the type of calculator you have, that might automatically stick you in an exponent, or you might need parentheses. If you're not sure, put the parentheses on anyways. You can never have too many parentheses. We want to make sure the calculator knows the entire exponent goes into the exponent. So I always put the exponent in parentheses. 52 times 3. Close the parentheses on the exponent. And when we hit enter, 2818.62. 2818.62 is the amount in this savings account at the end of the 3 years. Let's look at another one. Let's ask the question, how much should be invested at 11% compounded quarterly for 5 years to get $4,000. Again, when we see the interest is compounded, we know that formula is A equals P times 1 plus R over N, all to the NT power. Let's look at what we know in this problem. 11%, that's the interest rate of 0.11. That's good to know. We're compounded quarterly. How many quarters in a year? That's our N. N is 4. 5 years. That's going to be our time. The $4,000, though, is that the present principal value or the future accumulated amount? We want to get $4,000. That is the future accumulated amount. So A is 4,000 is equal to P, the principal, we don't know that, times 1 plus R, 0.11, over N, which is 5. Whoops, no it's not. N is 4, sorry. To the NT, 4 times 5. So we can put that in our calculator. Let's just do the parentheses part. We'll open up a parentheses, 1 plus 0.11 divided by 4, close the parentheses. The caret moves us into the exponent, and putting the exponent in parentheses, 4 times 5, and closing that. That part is equal to 1.72. 4,000 is equal to 1.72 times the principal. So we just need to divide by that 1.72 to find out what our principal equals. We'll take 4,000, divide, and again I want to get very accurate with this, so I'm going to grab the previous answer, the line right above, by hitting second, and then the negative sign gives me the A and S. 4,000 divided by the previous answer, which is 2325.00. Exactly, 2325. So if I invest $23.25, I'll have about $4,000 after 5 years. Let's do one more. Let's say a bank pays 9% compounded monthly. We're going to answer the question, what is the effective interest rate? Also known as the annual percentage rate, the APR. A lot of times a bank will say, we'll give you, our bank accounts pay 9% compounded monthly, and that's 9 point something else APR. Well, what does that mean? Well, let's take a look at that. What APR, the effective interest rate, is looking at is if the interest was paid annually, not monthly, how much would you make? And the way we're going to play with that is we're going to assume we're going to invest $1. You can pick anything, actually, and it works out just fine. But the $1 makes it the most obvious when we look at the final answer. So A is equal to P times 1 plus R over N to the NT. Our principal is going to be $1. Putting 1 in front of anything, you don't really have to write it. 1x is the same as x. So we're just going to say A equals 1 plus R over N to the NT. So our rate we see is 0.09. There's no time either. Remember we said annual percentage rate, effective interest rate. Time is always equal to 1 also. It's compounded monthly, so N equals 12. So the amount of that $1 is 1 plus the interest rate, which is 0.09, over 12, to the NT, which is 12 times 1. Well, 1 just makes it 12. So we end up with, open parentheses, 1 plus 0.09 divided by 12, close the parentheses, to the 12th power, is 1.0938. Now the 1 part here, that represents our principal that we started with. The extra stuff that we've earned this year is at the end. So if I write that extra stuff as a percentage, that's 9.38% effective interest rate. So 9% compounded monthly is the same as 9.38% compounded annually. One last type of interest I want to take a look at before we get away from lump sum interest and that is this thing called continuous interest. Continuous situations have to deal with when we have an infinite number of compounds. The interest is just continuously being put in the account. Some places where we see this type of situation is in inflation. When we say there's a 3% inflation, we're not saying that on January 1st, all of a sudden prices went up 3% overnight. No, the inflation is gradually increasing throughout the entire year. That's continuously growing. Another place you see it is population growth. Population growth is not compounded quarterly or monthly. People aren't born on the first of the month. They're born continuously throughout the entire year. And the equation that we're going to use for continuous interest, when we see the word continuous, that's going to be A equals PE to the RT. This is going to be our last equation we're going to take a look at today. Well, sort of. We'll talk about one brief one at the end. The new variable here is E. And E is kind of like pi. It's called Euler's constant. It's about 2.718, and it goes on forever. Fortunately, your calculator has an E button, so you don't have to really worry about what E equals. I'll show you here. If you hit second and then the ln, that gives you e to some power. We'll say e to the first power. That's just e. 2.7182, and it goes on. That's e. But let's look at how we can use e. Let's say $800 is invested at 7% compounded continuously for 4 years. Let's look at how much money is in this account. Well, when we see it's compounded continuously, that's our clue that we're going to use A equals PE to the RT. And here P, we start with $800, invested at an interest rate of 0.07, and our time is 4 years. So let's plug it in. A equals P, the 800, E to the R, which is 0.07, times T, which is 4. Just have to type this in our calculator. 800 E, and the way we get E, again, is second. And then above the ln is the E. That should automatically stick you in an exponent, automatically open up a parentheses, 0.07 times 4, close the parentheses if you have one. Enter, we've got 1058.50. 1058.50 is the total amount in this account after 4 years. Let's do another one. Let's look at effective interest rate again. What is the effective interest rate if 6% is compounded continuously? Whoops, where'd it go? There it is. Again, we see compounded continuously. That's our clue that we're going to do A equals PE to the RT. But when we're talking about the effective interest rate, we're going to take some shortcuts to figure out what that is. Remember, we say we're going to assume we're starting with $1 and we're talking about a time of 1 year. Essentially, that gets rid of the P and gets rid of the T. So all that's left is our interest rate, which is 0.06. So A equals e to the 0.06. On our calculator, hit second ln to get the e. 0.06 gives us 1.0618. 1.0618. Remember the 1, that represents the one we started with, the present value. The interest comes from the end. So the effective interest rate, instead of compounded continuously, if it was all paid at once, would be 6.18%. Now, a question people are often interested in with investments is, how long is it going to take for my money to double? I've got $1,000. I want to double my $1,000. Okay, well, let's look at it. Let's look at how long it will take an investment to double at 9% continuous interest. Well, we know we've got A equals PE to the RT. And we don't really care about the amount. We just want it to double. So let's say we start, I always like to start with 1 if I can pick whatever we want. If we start with 1, the final amount is going to be double that, which is 2. Now, I could use any numbers I want, but 1 and 2 are probably going to be the easiest to play with. We know our interest rate is 0.09, the 9%. And so we end up with 2 equals 1, which we don't need to write, e to the 0.09 times t. And so we're going to try and solve for t. Now, your textbook wants you to kind of guess and check at t. That is a pain, and it's going to take a long time. There's a much easier way to get at it. When we want to get at an exponent, we can use our logarithms. And you remember your logarithms from previous classes. If we have a base e, we're talking about a natural log. And then we can take the natural log of the answer will equal the exponent, 0.09t. Natural log means base e. And in class, if you want to review natural logs a bit, we can. But the way we can take base e is into a natural log of the answer equals the exponent. And that gives me something I can solve really quick by dividing by 0.09. So we get t is equal to the natural log of 2 divided by 0.09. We can do that on our calculator. Our calculator has a natural log button. We've been using second natural log to get the e, but just natural log gives us that ln of 2. Very important. You close the parentheses and then divide by 0.09. Enter the amount of time it's going to take for us to double our money is about 7.7 years. At 9% continuous interest, our investment will double every 7.7 years. Now, if we don't care about being as exact as this, we just want to know approximately how long it's going to take an investment to double. There's a nice little trick some financial people found called the law of 70. Also called the law of 72, because some people use 72, some people use 70. Depending on your context, one's better, the other's better. We're just going to do the law of 70. Same idea. The time it takes to double your money is approximately, and again, this is an approximation, it's going to be close, not exactly correct, 70 divided by the interest percent. So, since it's just an estimate, we're not going to spend much time on it, but I want you to see that problem we just did, how long to double at 9%. Well, that's just 70 divided by 9. And if you do 70 divided by 9 on your calculator, actually let's do it on the calculator here, 70 divided by 9, it's approximately 7.7777 years. Notice how close these two numbers are. It's a really good estimate that it will double every about 7 point, if we round, 8 years. And that's pretty darn close to what we found using logarithms. Now on the test, you're going to have to use the natural logarithm. But this is a nice little thing. I just want you to be exposed to the law of 70, also called the law of 72. Some people do 72 divided by 9. It's just an estimate, so it's probably just fine. So that's our simple interest and compound interest discussion. Take a look at your homework, come back to class with questions, and then next time we're going to get into the real fun stuff where we start to look at how you can save money and ultimately become a millionaire by the time you retire. We'll see you in class.